A very good afternoon, and let me welcome you all to this post-lunch session. I'm sure post-lunch session seems a little difficult, but we assure you that we're going to have a very, very engaging discourse on the topic that is going to resonate with today's celebration. And we have nonetheless a very eminent scholar like Dr. A. Satyanarayana Reddy, who is going to address you all regarding the topic pi and prime numbers. Before he delivers his address, I request the moderator of this session, Shri Sudhakar KB, Assistant Professor of Mathematics, Government Science College Autonomous Hassan, to kindly take over this session.
Thank you, ma'am. Good afternoon, everyone. Myself, Sudhakar, from Department of Mathematics, Government Science College, Hassan. It's a great pleasure for me to introduce Dr. A. Satyanarayana Reddy, who is going to deliver a completed MSc in Mathematics and MA in Education at Andhra University in the year 1995 and 1999, respectively. He obtained his PhD from IIT Kanpur in the year 2012. His main research areas are algebraic graph theory, linear algebra, and algebraic number theory. Sir has published more than 25 research articles in various national and international journals. He also presented more than 15 papers in national and international conferences. Sir has got first position for oral presentation on respectable graphs presented in a national seminar held at Brahmanand College, Kanpur in 2011. Sir has successfully guided 3 PhD students, and presently 5 students are pursuing PhD under him. He has been invited as a resource person in various academic activities. He has organized many national and international conferences and workshops. UGC is developing e-content in mathematics at PG level, where Sir is the e-content writer for number theory and graph theory. Sir is also a life member of different academic organizations, namely IMS, RMS, Academy of Discrete Mathematics and Applications, etc. He started his career as a lecturer in mathematics at Vikas Junior College, Kakinada, AP in 1995 and has more than 25 years of teaching experience. Presently, Sir is working as Associate Professor of Mathematics at Shiv Nadar University, UP. On behalf of students, faculty, and staff of Government Science College, Hassan, I once again welcome you, sir. Thank you. Over to you, sir.
Yeah, thank you very much. So, first of all, I am thankful to Sudhakar for introducing me, such a kind words. And I also thankful to Vinay Kumar for giving me an opportunity to speak here on the occasion of pi. So I hope my slides are visible.
Yes, sir, it's visible.
Yeah, okay. So as today's pi day, so on behalf of that, I choose this topic, pi and prime. So there is a connection between pi and prime that we will discuss. So, I'm asking a few questions to you. One of you can answer this. Let C and D are circumference and diameter of a circle respectively. Then what we can say about the value C by D? Any one of you? C is the circumference and D is the diameter of a circle. Then what is C by D value? You know 2 pi r is the circumference formula, right? So 2r is the diameter. So C by D is exactly pi, right? Okay. Similarly, A and R are the area and the radius of the circle respectively. Then A by R square is also pi, correct? So you know 4 by 3 pi r cube is, this formula is for what? 4 pi r square is what, right? So, and one of the beautiful identity, Euler identity, that is E plus I pi plus 1 is equal to. Can somebody help me that what is the value equal to? E power I pi plus 1. Okay. So this is one of the finest of the equations. So it has arithmetic, addition, right? Arithmetic, we have addition, multiplication, exponentiation. And also you can see that E power I pi plus 1 is equal to 0. So there are, what are the symbols which are involved here? One is E, I, pi, 1 and 0. You know 0 is additive identity, 1 is the multiplicative identity. Pi and E are related to logarithms, right? And I is the imaginary unit which is used to define complex numbers. So one of the beautiful formula, finest of the equations. So that involves pi. That's my point. Okay. So there are many places in physics they will use pi. So I will not go into that. So these equations actually minus infinity to infinity 1 by 1 plus x square is related to pi. I have not mentioned the values. You know these values. So for example, these are actually people do these in complex analysis course, right? By using residue theorem. Okay, these formulas you may have aware of, but instead of telling all of these, I'll take up one, in particular the last one, minus infinity to infinity power minus x square dx equal to how much? Okay, so Vinay, is it clear? My voice is clear, audible? Hello, Vinay. Hello, am I audible clearly?
Yes, sir.
Yeah, okay. Yeah, so in the group theory also, for example, cyclic groups, right? Cyclic groups are actually nth roots of unity you take, and with respect to multiplication, it's a group. There we will use pi also, correct? In the representation theory, pi occurs at many times. Okay, so in particular, now I want to discuss minus infinity e power minus x square dx value. Okay, so we know that this function f of x equal to 1 by root 2 pi e power minus x square by 2. So it is related to standard normal distribution in the probability theory. You are all aware. Since it is a distribution function, so minus infinity infinity 1 by root 2 pi e power minus x square by 2 dx equal to 1. Okay, which is equivalent to minus infinity e power minus x square by 2 dx is root 2 pi. How to prove this? Let us explore that. So actually, I want to evaluate the last integral, that is this quantity minus infinity to infinity e power minus x square by 2 dx, right? And I'm evaluating square directly. If it is square, then I can write product of two integrals like this. So it does not matter if I introduce new variable, correct? So then it is actually finally equal to double integral minus infinity to infinity minus infinity to infinity e power minus x square plus y square by 2 dx dy. Evaluating single integral like this is difficult. So I am taking the help of double integral. What is advantage of this? Now I can introduce the variables x equal to r cos theta, y equal to r sin theta. So then you can simplify it easily, right? So this becomes now e power minus r, x equal to r cos theta, y equal to r sin theta. Then you know Jacobian determinant dx dy equal to r dr d theta, correct? Then you will get this integral easily. So do you have any doubts, any one of you? So from that I got this minus infinity to infinity e power minus x square by 2 dx equal to root 2 pi. The one of the beauty of this equation is that it involves both e and pi, connection between e and pi. So can I proceed?
Yes, sir.
Yeah. Okay, so now I'll come back. So these are all related to pi. So this talk is about pi and prime. So this is about pi. Now I'm coming to the how the pi and primes are related in this slide. Later I will go more details. So this is called a characteristic function in number theory. So I am defining it as chi of n is equal to 1, n is congruent to 1 mod 4. So I am dividing the natural number n by 4. If the remainder is 1, then I'll put my chi of n value equal to 1. So somebody can help me, what is chi of 5 value? 5. What is chi of 5? So you know that 5 is congruent to 1 mod 4. So in that case, it is 1, right? When it is minus 1, when n is congruent to 3 mod 4. In the even case, it is 0. It is defined like that. What is chi of 10? it is 0 because 10 is an even number. It is divisible by 2. So our goal is to evaluate what is 4 times chi of n by n. Okay. So I just write down what is that we are having. Summation chi of n by n, right? So first value is n natural number. First value is 1, right? Chi of 1 is 1 because 1 is congruent to 1 mod 4. So 1 by 1. Okay. Next 2, chi of 2 is 0 because 2 is even. Now 3, it is congruent to 3 mod 4. So we'll get minus 1. Chi of n is minus 1. Chi of 3 is minus 1. We'll get 1 by 3. Next even. So 0. Odd 5. It is 1 mod 4. So chi of 5 is 1. So 1 by 5. So 1 minus 1 by 3 plus 1 by 5 minus 1 by 7, 1 by 9. Alternatively even and odd. Okay, there is a small mistake here. This is minus. Okay. I hope you understand. There is a small typo. Yeah. So how to evaluate this? What is this answer? I hope all of you know that 1 by 1 minus y is equal to 1 plus y square and so on. This is familiar to you, I hope. So then here I will put y is equal to minus x square. Then what is that we are going to get? Can you predict it? That is 1 minus x square plus x power 4 minus x power 6 and so on. Okay, hope it is clear to you. So, but we also know that the derivative of tan inverse x is 1 by 1 plus x square. So 1 by 1 plus x square now becomes, now if I now differentiation is this, if I integrate, you understand that 1 by 1 plus x square is 1 minus x square plus x power 4 and so on. So if I integrate it, right, 1 becomes x square by 2, x square becomes x cube by 3 and so on, right? In that if I substitute 1, what is tan inverse of 1 now? Tan inverse of x is this series, right? In that if I substitute 1, what happens? Tan inverse of 1 is 1 minus 1 by 3 plus 1 by 5 and so on. Now you know the value of tan inverse 1. What is the value of tan inverse 1? I hope you know the tan inverse 1, correct? Any one of you can help me?
5 by 4.
5 by 4. So now that is equal to pi by 4. So I asked for 4 into. So the answer is equal to 5. You see, is it not beautiful that 1 minus 1 by 3 plus 1 by 5 minus 1 by 7 plus 1 by 9 minus 1 by 11 and so on, odd numbers, alternatively positive, negative. That is equal to 4 times pi by 4. Answer is pi by 4. 4 times of this is pi. Okay, but of course here there are prime numbers, composite numbers, all are there, all odd numbers are here. But how to prove this one? Where primes will come? Actually, you can see that I can write this as a product of primes. I will give this proof later. So by fundamental theorem of arithmetic, every natural number can be written as product of primes. From that, I can write this equation. Okay. So this I can replace it as in terms of the product of primes. So there we'll get this equation. Primes and pi are related. Okay. So I will explain you more about these summation and product formulas. That is called Euler product formulas that I will introduce in a while. Okay. Yeah. So now coming to the primes. So how many primes are there? You all know there are infinite number of primes, right? So do you know any one of you how to prove it? How to prove that there are infinite number of primes? Okay. So generally these people believe that this is the first proof given by using proof by contradiction. Suppose there are only finite number of primes, right? Assume that there are only finite number of primes, 2, 3, up to some number. These are the only primes. Then what we will do? We will multiply them, add plus 1 to that. Now, that is a natural number and greater than 1, right? But we know that every number greater than 1 has a prime factor. That has a prime factor. But these are the only primes. I took first few primes. So I'll get a contradiction that prime is going to divide 1. I'll give the proof now. Okay. Suppose there are only finite number of primes, say P1, P2, and so on, Pk. Correct. So I will now construct this number. Let P is equal to P1 into P2 into Pk plus 1. Right. Now, by fundamental theorem of arithmetic, P has a prime factor. So Pi divides P, right? But we know that, so if Pi divides P for some prime, right? Then Pi divides P minus 1 also. Because Pi is 1, P1 into P2 into Pk, right? These are the only primes we are assuming, but it has a prime factor. If that is one of them, then Pi divides P as well as Pi divides P minus 1. So Pi divides P, right? Pi divides P and Pi divides P minus 1. From these two, I'll get Pi divides 1. That is a contradiction. Prime cannot divide 1, right? That means what is that we have? So P has a prime factor, which is different from these. But I assumed that these are the only primes, but now I'm producing a new prime. That's why there are infinite number of primes. Is it okay? Is it clear? Any questions? Can I proceed?
Yes, sir.
Okay. So now you know that harmonic series, summation 1 by n, it diverges, right? So how to prove? There are different proofs are there. I will give one proof and I will skip one. One of the proof is that you know that 1 by 3 plus 1 by 4, which is greater than or equal to 1 by 4 plus 1 by 4, correct? Hope it is clear to you. 1 by 3 is greater than 1 by 4. 1 by 3 is greater than 1 by 4. So, in fact, not greater than or equal to, in fact, greater than. 1 by 3 plus 1 by 4 is greater than 1 by 4 plus 1 by 4. That is equal to 1 by 2. So, similarly, 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8. That is greater than 1 by 8 plus 1 by 8 plus 1 by 8 plus 1 by 8. Because 1 by 5 is greater than 1 by 8. 1 by 6 is greater than 1 by 8 and so on. But if I add 1 by 8 4 times, I'll get 1 by 2. Right? Like that, if I start from 2 power k minus 1 plus 1 to that, I'll get the sum is greater than or equal to 1 by 2. Hence, I can write summation 1 by n, that is 1 plus 1 by 2 plus 1 by 3 plus 1 by 4 and so on. I am grouping them. 1 plus 1 by 2. 1 by 2, 1 by 3 and 1 by 4 is one group. 1 by 5 plus 1 by 6 plus 1 by 7 plus 1 by 8 is one group. Like that I group it. But each of them is greater than 1 by 2. So 1 plus 1 by 2 plus 1 by 2 plus 1 by 2 and so on. If keep on adding, I'll get infinity. So it is diverges. It is not a very complete proof. I'm just informally I'm telling you how can I prove it. So this is what I'm telling, right? I'm now giving the picture here. Hope this is clear to you, this picture. Is it clear to all of you?
Yes, sir.
Yeah, good. So this is diverges. There is another proof also. I will come back to this if time permits. Actually. So if time permits, I will come back later. So, so for example, we have, yeah. So this is another proof. I will come back to this at later stage. This is another one. By integration, right? So now I'm giving another proof. This is needed. I'm giving a different proof now. Infinitude of primes. Okay. So go slow. We'll go slowly here. So P is a prime number. So like P is equal to 2, P is equal to 3 and so on, right? So I am taking 1 plus 1 by P plus 1 by P whole square plus 1 by P whole cube and so on, correct? Yeah. So now this is actually which series it is? 1 plus 1 by P plus 1 by P whole square and so on. Somebody can help us that which series it is? 1 plus 1 by 1 plus R square plus R cube and so on. Which series it is? 1 plus R square plus R cube and so on. It is a geometric series, correct? So you know geometric series sum, it is 1 by 1 minus R. Now my R value is 1 by P. That is less than 1. So it is converges. And the value is 1 by 1 minus 1 by 2. or otherwise 1 by 1 minus 1 by theta inverse, right? So I hope this part is clear, right? In general, if I take p power s, s is greater than 1 plus 1 by p power s plus 1 plus p power s whole square and so on, that is equal to 1 by 1 minus p power s by using geometric series, right? So Euler stated a fundamental theorem of arithmetic in terms of the harmonic series. That is now we called Euler product. Because of Euler product, many new functions were introduced like Riemann-Zeta function, Dirichlet functions and all. I'll tell you what is Euler product. So this is what Euler product. So introduced in 1937. What is that? Zeta of s is equal to summation 1 by n power s. So s equal to 1 harmonic series 1 by n only, right? Now this is equal to, look at here, one side I have summation, other side I have a product. Okay. So how these two are equal? Now that is the question, right? This is exactly comes from the fundamental theorem of arithmetic. What is the fundamental theorem of arithmetic? Every natural number greater than 1 can be written as product of primes. Correct? How he used it to prove this result? I'll explain you that. What is zeta of s? Riemann-Zeta function. This is actually called Riemann-Zeta function, but I will define it later. Zeta of s, how I defined? Summation 1 by n power s. What is that meaning? 1 plus 1 by 2 power s plus 1 by 3 power s plus 1 by 4 power s and so on. Okay. Right. Okay. Why this is equal to product? It's like this. Why it is? Okay. So to explain you, right? So look at that. What is the first prime we have? First prime is 2. So 1 plus 1 by 2 power s plus 1 by 2 power s whole square and so on. That is exactly that 1 by 1 minus p power s we introduced earlier. So second prime is 3. Next prime, like that products will be there. Why? But why these two are equal? That's the question, right? So, right, you can see here, you can understand there is a color here. 1 by 30 power s. 1 by 30 power 30 is what? 30 is equal to 2 into 3 into 5, right? I give that color. This is equal to 1 by 2 power s into 1 by 3 power s into 1 by 5 power s, right? Here I have summation, but 1 by 30 power s, 30 is actually product of primes, 2 into 3 into 5. So I written as a product of primes now, right? So this is infinite sum, but again, there in between there is a product, right? That is what this is. Is this part clear? This is important for us for today's talk, today for our discussion. So zeta of s is 1 by n power s, that is this, and I'm explaining you that why this is summation equal to product, right? 1 by 30 power s, I'm explaining with one example. 30 is 2 into 3 into 5, right? So I hope you can see my cursor also. Am I correct? Vinay sir, can I see the cursor?
Yes, sir. Yes, sir. Yes,
Yeah.
sir.
Yeah, so 30 power s I am writing as 1 by 2 power s into 1 by 3 power s into 1 by 5 power s. Can you somebody help me that how 1 by 80 power s can be written? 80 power s. 80 is equal to, you know that, right? Yeah, okay. So 1 by 2 power 4, right? Yeah, okay. You can figure out that. So this is the formula. Okay, this is called Euler product formula. If S is a complex number, then we'll call a Riemann-Zeta function, right? So in particular, what is zeta of 1? So recall again, what is zeta of S? Okay, zeta of S is equal to summation 1 by n power s. What is zeta of 1? Okay, zeta of 1 is 1 by n, right? But 1 by n is equal to now product of primes. Okay, now from this, how do you know that the product number of primes are finite? That is my goal. Okay, suppose there are only finite number of primes. Then what happens to this quantity? How many products will be there if there are finite number of primes? See, 1 by 1 minus 2 inverse. Next number is 1 by 1 minus 3 inverse. If there are only finite number of primes, then this is a finite quantity. That means summation 1 by n is a finite quantity. But we know that summation 1 by n diverges. So primes are infinite. That is what I'm saying. Okay. So by using summation 1 by n diverges, we are proving that primes are infinite. Okay. Now I will bring that how it is connected to pi in a while. Okay. I hope it is clear. Riemann zeta function. Yeah. Okay. So it's a contradiction. So number of primes are infinite. Okay. Now let us look at this summation 1 by n square. That means s equal to 2. That is zeta of 2. This is a very famous problem called Basel problem. Okay. So this is proposed by Bernoulli. You know that there are so many Bernoullis. Bernoulli is a big family of mathematicians. So there is a one person called Daniel Bernoulli. He asked this question that what is summation of 1 by n square? So it is equal to how much? They know that it is converges, but what is its value? It is simply that 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on. So almost 70 years, no one touched it. Then someday Euler gave. Okay. So that problem is stated in Basel in Switzerland. That's why it is called Basel problem. But after many years, Euler completed given the answer. It is pi square by 6. You see the beauty that one side we have natural numbers 1 by 1 square and of course fractions. Means all are rational numbers. Other side we have suddenly pi is coming. How it is, right? So okay, so that is the thing. So I will prove it in a while. Summation 1 by n square, or that is zeta 2 is equal to pi square by 6. I will prove in a while. Right now I can use it. Okay. So this is very useful. So I'm stating one small problem related to this. So that is related to pi again, correct? Suppose x and y are chosen randomly from natural numbers. So two random natural numbers I choose. What is the question? What is the probability that their GCD is 1? Easy question, clear? I took two numbers, natural numbers randomly. What is the probability that their GCD is 1? I'm calling that as capital P. Okay. So this is our goal to figure out. Okay. So this problem, to solve this problem, I am asking another question. The question is that, so suppose that GCD of x comma y equal to n. Okay, for a natural number n. So let us say n equal to 10. What are all integers for which GCD of x comma y equal to 10? Right? That is if and only if. So what is the meaning that GCD of x comma y equal to n? N has to divide x, n has to divide y, and that is the largest integer dividing both, correct? So that we can write in equivalently as x is congruent to 0 mod n. That means n divides x, right? So there is a mistake, sorry, this is y. Okay, there is a typo. So this is y congruent to 0 mod n. Okay, I hope it is clear to you. So one is x congruent to 0 mod n, second one is y congruent to 0 mod n. And third condition is this is the largest integer. So that is equivalent to GCD of x by n comma y by n is equal to 1. So GCD of x comma y equal to n is related to this. But when you divide x by n, what are the possible remainders I have? 0, 1, 2, up to n minus 1, right? So what is the probability that x is congruent to 0 mod n? Exactly 1 by n, right? I hope it is clear. When you divide an integer x by n, what are the possible remainders? 0 to n minus 1. How many remainders are there? N remainders are there. But I am imposing that x is congruent to 0 mod n. What is the probability that if I choose randomly an integer, what is the probability that it will give remainder 0? Exactly 1 by n. Y equal to 0 mod n also 1 by n, right? So probability that x comma y GCD is equal to n now becomes p by n square. Why n square? X equal to 0 mod n 1 by n. Y equal to 0 mod n 1 by n. They are all independent. And the probability of two numbers GCD, I am already assuming it is p. So p by n square, right? So because of these things, now I have this part. What is that? So if I take any two integers, then what is going to happen? So GCD is one of the natural number, right? Okay, so I am collecting all things. Summation n is equal to 1 to infinity. GCD of x comma y equal to n. So For any two integers, some n will be there, GCD as a GCD. So the summation is equal to 1. But this is equal to P by n square. So P is fixed quantity. I'll bring it out. So this is 1 by n square, that is equal to P times zeta 2. This is exactly zeta 2. So now what is the P value? P is equal to 1 by zeta 2. So you see now in this slide itself, P is the probability of randomly chosen two numbers whose GCD is 1. Now that probability is equal to 1 by zeta 2, but zeta 2 is related to pi square by 6. So what is the probability of two randomly chosen integer GCD 1 is related to pi. Okay, that is what I want to convey. So I give few seconds to go through, and if you have any questions to ask. Okay. In fact, there are there are many problems like this. If I in XY plane, I put the grid, that is lattice points, 0, 0, 1, 1, 2, 2 integers, -1, -2. So what is the probability that I can see 0, 0 to other lattice points? From 0, 0, which one are visible? That is exactly their GCD is 1. So what is the probability that a point is visibly also related to pi? Okay. So can I proceed?
Yes, sir.
Okay. Actually, Dirichlet later extended this one to. Actually, Dirichlet goal is that if you take, you know that there are infinite number of primes of the form 4k plus 1. There are infinite number of primes of the form 4k plus 3, like that. If you take any arithmetic progression, a plus bn, where a comma b is GCD 1, then you prove there are infinite number of primes in that arithmetic progression. But to prove that one, the first proof given by Euclid, that the first proof given by Euclid by contradiction, that may not work. Euler product formula is useful. For that, he introduced these characters and all. Okay, so a lot of complex analysis also developed. So the wonderful area. So Euler product formula is very, very beautiful thing. It helped to prove many other results. Okay. Yeah. So yeah, I'll just skip that. But by using this only, zeta of 2k completely figured out. See, zeta of n, I asked you to remember. Zeta of s. Zeta of s summation 1 by n power s. Right? So we already checked that zeta of 2. Zeta of 2 is exactly pi square by 6. Zeta of 2 means summation 1 by n square. Right? What is zeta of 4? Zeta of 4 is summation 1 by n power 4. Right? So all evenness are completed. Zeta of 2 power 2k. Complete clean formula is available. That is pi power 2k. See, you see that interestingly pi is came here. That is what I want to tell you, right? But here these B2k are called Bernoulli numbers. Bernoulli numbers comes from this infinite series. Okay, it's a generating function. T by e power t minus 1 is generating function, exponential generating function for the Bernoulli numbers. Okay, that you don't need to go that far. But what my point is that zeta of 2k value related to pi. That is what I want to convey, right? So later, Appari in 1978, he computed zeta of 3. He told that it is irrational. But still, it is very little known for zeta as S is odd. Even you do not know. We know it is converges, but it converges to rational or irrational. That also not known. Even zeta 3 exact value is also not known. For odd, it is very tough. So still they are open. Yeah. So I'm now going further. So now my goal is to show this formula. Okay. Summation 1 by n square is equal to pi square by 6. Okay. Okay. So 1 by sin square x. Sin x is 2 sin x by 2 cos x by 2. So sin square x is 4 sin square x by 2 cos square x by 2. Correct. So, and you know that this can be written as, you can simplify this quantity. Cos square plus sin square is 1. So you'll get it. I hope it is clear. from here to here. Okay. Now, now I have here sin square x by 2 and cos square pi by 2 I can write as sin square pi plus x by 2, right? Like that, if you keep on simplifying, right? This sin square x by 2 again I can write, right? So I keep on doing this. So you know that the sin pi by 2 is 1. Sin square pi by 2 is also 1. So 1 is equal to, if you keep on writing beautifully like this, then you will get this summation, right? And you know that n sin x by n is equal to x, right? By using this, we'll get this summation, this one. Okay, that is summation k is equal to 0 to infinity 1 by 2k plus 1 whole square. So what is the summation? Can somebody help me? K is equal to 0 to infinity 1 by 2k plus 1 whole square. What is the first term here in the summation? 1 by, when k is equal to 0, we'll get 1 by 1 square. Okay, when k is equal to 1, 1 by 3 square. So 1 by 1 square plus 1 by 3 square plus 1 by 5 square plus 1 by 7 square and so on is equal to pi square by 8. That we got from this approach. Okay, so this is I written here 1 plus 1 by 3 square plus 1 by 5 square and so on equal to pi square by 8. Okay, you see that odd numbers, only odd numbers square sum is equal to pi square by 8. But now if I multiply it, what are missing? Even terms are missing. That means 1 by 2 square plus 1 by 4 square and so on. This quantity we know by geometric series, it is 4 by 3. So if I multiply these two, I'll get this, right? This into this is equal to, this is 4 by 3, but this is pi square by 8. So I'll get pi square by 6. Am I clear? You can stop me whenever, if there is a clarity, if you need some more, I want to show me more slides here. You want more time, please stop me, I can discuss. But please let me know now, can I proceed or not?
Yes, sir, it's clear.
Yeah, okay. So that is what we done, 1 plus 1 by 2 square plus 1 by 3 square and so on, that is equal to pi square by 6. Yeah, so this we proved. Now I will use this to prove many other results. Okay, even if you not understand the proof, so if you take this 1 plus 1 by 2 square plus 1 by 3 square and so on equal to pi square by 6, you know that this is proved by different ways. One is people use Fourier series also. Okay, yeah, okay, now come back to this. Now by using this, how can I prove other identities? Let us explain one. 1 plus 1 by 2 square plus 1 by 4 square plus 1 by 5 square and something is there. You see this in this summation, what are missing? Are you able to find out? Look at that. 1 plus 1 by 2 square, 1 by 4 square, 1 by 3 square is missing. Figure out. 1 by 5 square is there, 1 by 6 square. 1 by 9 square is missing. I hope you understand. Okay. But can I find the sum equal to how much? That is the question, right? And I will show that it is also related to pi. How? So this series I multiply by 1 by 3 square plus 1 by 9 square and so on. But this is again a geometric series with R value is 1 by 9, right? 1 by 3 square, right? So this is equal to 9 by 8. If I multiply this to this, right, then I will get this quantity. Because again, I will get the previous quantity, 1 plus 1 by 1 square plus 1 by 2 square plus 1 by 3 square and so on. Finally, we'll end up S is equal to 4 pi square by 27. So this series 1 plus 1 by 2 square plus 1 by 4 square and so on, all multiples of 3, in particular powers of 3 are missing. That summation actual value is equal to 4 pi square by 27. I hope it is, you may like it. This one. Similarly, I can look at that series where are multiples of 2 and 3 also missing. Okay, 1 plus 1 by 5 square, 1 by 7 square and so on. Okay, that exactly the same way you can do it. You can figure out. I am not giving the answer for this. I am leaving it to you. Okay. So another Euler identity due to Euler is 1 plus 1 by 2 power 4 plus 1 by 3 power 4 and so on. You see that S value is 4. That means zeta of 2 into 2. We already gave the formula, right? It is equal to pi power 4 by 90. Okay. Look at this carefully, and by using Euler product formula earlier we discussed, right? This I can write as a product of these quantities, right? This 1 plus 1 by 2 power 4 plus 1 by 3 power 4 and so on. This is summation. It is a product form. Product. In only primes will come, right? So this is equal to 1 by 1 minus 2 power 4, 1 by 1 minus 3 power 4 and so on. It is equal to pi power 4 by 90, right? But what I do here, okay, Ramanujan observed the nice things from this point onwards. 1 by 1 minus 2 power 4, what he done? You can see, right? 1 by 1 minus pi power 4, I can write it as 1 by 1 minus x square, right? 1 plus x square into 1 minus x square, correct? You can write like this, correct? So I can write these things like this now. 1 minus 1 by this one, product like this, pi square by 90. Now I will bring 1 by 1 minus 1 by 2 square, 1 by 1 minus 5 square, 1 by 1 minus 3 square, 5 square are together one place, right? So that is actually, you already know, that is exactly the pi square by 6. So now this quantity is equal to pi power. So by multiplying the pi square by 6 to here and by cancelling, I'll get pi square by 15. But this summation, you know 1 by 1 plus x formula, right? X is 1 by 2 square, like 1 by 3 square. So this is what. Now we go backwards, right? We have this summation. So this is clear to you. So if you simplify this, we will get this 1 by minus 1 by 2 square plus minus 1 by 3 power square plus 1 by 4 square, 1 minus 5 square, 1 plus 6 square. So 2 times minus plus, like that things will come. You multiply and check, you will get this quantity. But earlier what we have, 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4, all are plus. What is the answer? Can somebody help me? 1 plus 1 by 2 square plus 1 by 3 square plus 1 by 4 square plus 1 by 5 square and so on. That is equal to how much? That is pi square by 6. So add these two. Ramanujan finally is, subtracted these two, that one and this one. Then when you subtract, 1 gets cancelled. Okay, 1 by 2 square will be there. Okay, 1 by 3 square, 1 by 5 square. Okay, when minus signs are there. So this, so he subtracted pi square by 6 minus pi square by 15. We got it as pi square by 20. Okay, in this series, you can see that in this series, all natural numbers with even number of prime factors has deleted. Hope it is clear to you. Why? Okay, let us see. So 11, how many prime factors it has? Not 11 square I am talking, 11 has only one prime factor. 8 you take, 8 how many prime factors it is? 2 into 2 into 2, so 3 prime factors, right? 7 is divisible by 7 only, only one prime factor. 18 for example, I gave here. 18 is equal to 2 into 3 into 3, product of 3 primes. So if you look at any term in this series, each denominator, that is the product of exactly odd number of primes. That means this series does not contain terms which have even number of prime factors. So that answer is equal to pi square by 20. I hope you may like this, right? So that, okay, so my goal today is that Euler product formula, primes, and there are so many series which are related to pi. We can manipulate so many things. I am just showing few of them. Any questions? Yeah. Okay. Yeah, so this is what I want to show. Thank you very much. I just completed within 15 minutes gap so that you can ask some questions. Yeah. Thank you for your patience. Yeah, now questions. You can ask any question.
Thank you, sir. Participants, you can post your questions in the chat box.
Chat box, I cannot check actually, but anyhow, I'll see. For that, I have to stop sharing. Yeah. So, pi square by 6. Okay, yeah, people are answering actually my questions. I'm not checked while I'm teaching. I'm lecturing. I'm not able to see that these answers. And thank you. Thankful to you people. So you are answering that. Yeah. But I do not see any questions as such. How the value of pi is 22 into some of the determinants. Now, see, pi value is not 22 by 7. Okay, it is approximate value. Pi is not 22 by 7. In fact, there is a thing that you can check actually. Pi value has infinite number of digits. Okay, so people are actually looking for how. So today, why pi day? Can somebody help me? Today, why it is called a pi day? 3.14. So March 14th, right? That is the reason that 3.14. So 14th March, right? Yeah. So actually, this is not the value of pi. So pi is an irrational number. Irrational number, so it has actually infinite number of digits. It is not recurring. It is continuously goes away. Right. Now you can see that people are looking that 31 is a prime number. 3.14. Let's forget about dot. 31 is the prime number. Like that. So people are looking that in this expansion, what are primes? So consecutive digits. So still it is an open problem. How many primes are there? What are all primes in this expansion of pi? Yeah. Okay. So I hope I answered you. It is not exactly 22 by 7. 22 by 7 is the approximate value. Hope I answered your question. Yeah. Any other questions? Okay. If there are no questions, thanks to you. Thank you very much for giving this opportunity.
Okay, thank you, sir. So that was an insightful session regarding relationship between pi and primes. On behalf of students, staff, and faculty of Government Science College, Hassan, I would like to thank you, sir. Thank you very much.
Thank you.
Thank you, Sudhakar sir, for being the moderator of this session and doing the formalities. And I once again express a very hearty thanks to Dr. A. Satyanarayana Reddy for his very interesting and intriguing session. And I could see all of my colleagues here being completely engaged in your talk, sir. On behalf of GSC family and the Department of Mathematics, express a special thanks to you for joining us today. Thank you, sir. And now I think it's time for us to acknowledge and express gratitude to all of them who have put their best to make the webinar a successful one. And to do the same, I request my colleague, Dr. Kumar Hetsi, Assistant Professor of Mathematics, to express vote of thanks.
Thank you, madam. May I audible?
Yes, sir, you're audible.
Yes,
Good afternoon, one and all present here. I am Kumar Hetsi, Assistant Professor, Department of Mathematics, Government Science College, Hassan. Now I am going to summarize the sessions that are being there with in the morning. The first session was handled by Xavier James Raj, sir. I has begin with the definition of research, the space research, and explained the importance of mathematics and mathematicians in space science. The second session was handled by Dr. Chandrashekhar BM. He explained about the basics of number theory, and he has proved many properties using the LUB properties, and also has proved Archimedean property and dense properties of the real numbers. The third session was handled by Dr. A. Satyanarayana Reddy, sir. He explained about pi and primes, and he connected the relation between Euler constant E and pi, and he proved that the primes are infinite, and also he proved that harmonic series are divergent. So now we are at the verge of today's webinar. It gives me an immense pleasure to deliver a vote of thanks to all the dignitaries, participants, and personals who have contributed for the successful execution of this webinar. I would like to thank Dr. Xavier James Raj, former scientist ISRO and presently serving as president of Annai Velankanni College, Tholayavattam, who delivered an erudite talk on application of mathematics in space science. Mathematics being abstract, no one can feel its application directly as the other disciplines that have. But your disclosure on application of mathematics in the space science was imprinted in the minds of the participants with absolute clarity. Thank you very much, sir. Pi is not a just collection of random digits. Pi is a journey. Pi is an experience. Unless you try to see the natural poetry that exists in pi, you will find it very difficult to learn. Dr. A. Satyanarayana Reddy sir beautifully explained about pi and primes, their importance. On behalf of our college, Department of Mathematics, and all the participants present here, I would like to thank Dr. A. Satyanarayana Reddy sir, Associate Professor, Department of Mathematics, Nadar Institute of Eminence, UP. Thank you, sir. I would like to thank Dr. Chandrashekhar BM, Assistant Professor, Department of Mathematics, Dr. G. Shankar, Government Women's First Grade College and PG Center, Udupi. He enlightened us about LUB properties and its applications. Thank you, sir, for accepting our invitation and spending your precious time with us. And we proud to say that you are alumni of our college. Sir, we are having alumni association in our college. I request you to take part in that association because we need eminent personalities like you, sir. I would like to thank our beloved principal, S.H. Gangegowda, who is constantly supporting our department in all our endeavors. Thank you, sir. I am running short of my words to express my humble thanks to our head, Dr. Vinay Kumar PN, who is the backbone of this event. Sir, you have beautifully organized this webinar and guided us in conducting and making this event a grand success. Thank you, sir. And I would like to thank Madhushri, Head, Department of English, for coordinating today's program. Thank you very much, madam. I thank all my colleagues, teacher participants from Karnataka and also outside the Karnataka students for making this event successful. Thank you one and all. And kind attention participants, it's made mandatory to fill and submit the feedback form to get the e-certificate of the webinar. Hence, I request all the participants to fill and submit the feedback form to get the e-certificate of the webinar. Thank you very much. Over to Madhushri, madam.
Thank you, sir, for extending thanks to everybody who worked behind this webinar. And with a congratulatory note to Professor H.H. Gangegowda, Honorable Principal of our college, and very hearty congratulations to Dr. Vinay Kumar for hosting this very, very interesting webinar, and his colleagues from the department, on all of them who have supported us in this endeavor. A huge thanks to one and all from the family of GSC Hassan to you all. And before we call the curtains down to this webinar, I once again request, and it's a reminder, that all the participants have to fill in their feedback forms to get their e-certificates. And please remember that it will reach you within 3 to 4 days of this seminar. So thank you all, each and everyone who have participated in